So as an example, let's look at some numbers. So we're going to look at a uniform plane wave that's traveling in seawater. We're going to assume that the XY plane is just below the sea surface and that the wave is traveling in the Z direction into the water. The parameters of seawater are that the relative dielectric constant is 80. The relative permittivity is mu is 1, and sigma is 4 Siemens per meter. So starting with zero phase at z equals 0. So in other words, or starting at z equals 0 with the following expression. So here is the magnetic field at 0 and t. It's in the y direction. It has a magnitude of 100. The frequency of the wave is 2 pi times 10 to the third, and the phase angle for h is 15 degrees. So now we want to obtain expressions for E and H, and then we want to find the depth at which the magnitude of E is 1% of its value at z equals 0. So since H is along Y and the propagation direction is Z, E must be along X. So the general expressions for the phasor fields are given as follows. So here's E and here is H, with alpha and beta being as we defined them in the previous lecture, and eta once again being complex because we're in a lossy medium. So epsilon prime over epsilon double prime is sigma over omega epsilon. That's 9 times 10 to the 5th. So the question is, then what does that mean? Is it a good conductor or not? Yes, this qualifies seawater as a good conductor at 1 kilohertz. So we can use the good conductor expressions that are given in table 7.1. So let's go back to table 7.1. And let me draw your attention to this statement at the bottom. In free space, epsilon's epsilon naught, mu is mu naught. In practice, a material is considered a low loss material if sigma over omega epsilon is less than 0.01, and it's a good conductor if epsilon double prime over epsilon prime is greater than 100. So when we want to determine which of these approximate expressions we can use, then we want to do these little tests on our material at a given frequency. So back to our test here, epsilon prime over epsilon double prime is 9 times 10 to the 5th. So that means we are a good conductor at 1 kilohertz. So we can use the good conductor expressions, which means that alpha is the square root of pi f mu sigma, and beta is equal to alpha. So we get 0.126 for alpha and 0.126 for beta. And then from that table for eta, we get 1 plus j times alpha over sigma. So if we plug these things in for eta, we get the following expression, 0.44 e to the j pi over 4. So now all we have to do is plug in. So basically, our electric field looks like e to the minus alpha z, e to the minus j beta z, e to the j omega t. And then we have this e to the j phi sub 0. So when we now put that into the time domain, our e to the minus j beta z becomes e to the minus 0.126z. That's beta was calculated on the previous page. Or alpha was calculated on the previous page. Here's beta, also calculated on the previous page. Phi naught at the moment is not determined. So H basically would then be the real part of the electric field, or it would be, the real part when we go to the time domain, electric field divided by eta. So this is eta. So when we take the electric field divided by eta and we plug in all the terms, this is the expression that we get, expression 7.80b. So now you might remember that given in the problem, our phase angle was 15 degrees. So if you look at the phase angle that we got when we calculated from the electric field, what we got was phi sub 0 minus 45. So that would make phi sub 0 minus 45 would have to equal 15. So phi sub 0 would have to equal 60 degrees. So going back then and substituting everything in, here's our magnetic field that was given. Here is our electric field that was determined. So now what depth will the amplitude of the electric field have decreased to 1% of its initial value? So if we look at how it behaves exponentially, we have e to the minus 0.126z, and we want to know when that is equal to 0.01. So basically, if you take the natural log of both sides of this expression and then solve for z, you get the following. So 37 meters. So even though seawater is considered a good conductor, you're still about 100 feet, 37 meters, into the seawater before the amplitude of the electric field has decreased to 1% of its initial value. This is an illustration of what the electric and magnetic fields would look like as a function of z. Okay, now let's look at another example where we have DC versus AC current flows in conductors. So in the DC case, basically the current is distributed equally across the conductor because the frequency is 0. But when you have an AC case, because the electric fields die away exponentially as you enter the conductor, and the conductor is not a perfect conductor, but it's a good conductor, basically the current density is highest around the wire's perimeter. And the depth at which the current density exists is basically equal to the skin depth. So if we have a conductor with E naught at the surface, and remembering that J is equal to sigma E, we can basically calculate what J will be as a function of Z. And then we can find a total current that crosses a given YZ plane by taking the integral across the surface with respect to Z. So basically the current does decay exponentially as you enter the conductor. And basically you will get a constant current, or you can estimate that this is equal to a constant current density J naught that flows through the section del S. So this is pretty commonly done. Here is our expression for J, where we basically took expression for the electric field, substituted in for alpha and beta for a good conductor to get things in terms of omega and the skin depth. So here is what the current density looks like, or the current looks like in that wire. So this is a fairly common thing, and it has to be taken into consideration when you're calculating or determining the resistance of a wire. So normally we would say the resistance of a wire is rho L over A. But when we do that, we're making the assumption, if we go back, we're making the assumption that the area is the area across the wire. However, in the AC case, if the frequency gets high enough, it turns out that it's possible for the current only to flow along the surface of a conductor or penetrate a very small amount into the surface. And in that case, the resistance of the wire is quite different. It's rho L over A, but A is not the entire area of the wire. It's the area of the ring on the outside of the wire where the current is flowing. And that's typically approximated as the skin depth.